Okay, this is round 2 of our weak acid, weak base calculations. And this example is calculating the pH of a weak base solution. So the setup for this is identical to our weak acid solution, except in this case, we're calculating the OH minus concentration as X. And so that's the square root of the Kb times the total base minus C, which again would be the OH minus concentration. And we're going to set up the same iterative approach where we're going to assume that the OH minus concentration is initially 0. We will substitute that 0 in to our expression for X to calculate the OH minus concentration. And then we're going to set cell D27 equal to D26, and that creates the iterative process to compute a better value for OH minus. So I will start by doing that. So let's begin with sort of a general layout of the spreadsheet. Total concentration of base 0.01, 10 millimolar. pKb is 5. That means my pKb is 10 raised to the negative B26. We'll come and talk about these stars in a second. My OH minus is equal to BH plus, so I'm, in this case, assuming that my base is neutral to form the cationic form as the acid. And again, here's my equation. Square root of B28 times B25, the total base, minus D27, which initially is set to 0. So now I'll go ahead and say, but D27 really isn't 0. It's really the OH minus concentration from the first step of the iteration. And we are done. Okay, so this iteration has worked. And the BH plus concentration is 3.1 times 10 to the minus 4. The OH minus concentration is 3.18 times 10 to the minus 4. My B concentration we compute by mass balance. Total base minus the acid form gives me the unprotonated form. H plus is computed from the Kw, and I have an error here. It should be Kw star divided by the OH minus concentration. And finally, I've added in mu, which is the ionic strength. So the ionic strength, you remember from previous videos, is a half times the concentration of all of the anions and cations times their charge. These are all plus or minus 1 species, so I've eliminated or ignored the z squared term. So ionic strength in this case is around 0.3 millimolar. So why do I want to compute the ionic strength? I want to compute the ionic strength because it allows me to introduce activity coefficient corrections into this problem. If I want to turn those off, I can just set the ionic strength term to 0, and it will then compute it without activity coefficients. But if I set this term to anything other than 0, it will now allow me to calculate the gammas. I haven't labeled that, so I'll put that in. And this gamma is for BH+. My gammas are defined in terms of the ionic strength, the ion size parameter, and you can see because my ionic strength is relatively low, my activity coefficients are very close to 1, 0.979, 0.979, and then the activity coefficient for the proton is 0.98, again, depending on the ion size parameter. So now that I have these activity coefficients, I can update my values for Kb in terms of Kb star. So if we click on cell B28, we'll see that B28 is Kb times the activity coefficient of the amine, in this case NH3, so it's just a simple inorganic species, divided by G28, which will be the OH minus activity coefficient, and G29 is the, see, that should be OH minus, there it is, 28 and 29, the activity coefficients of BH plus and OH minus. And notice that the The neutral species has an activity coefficient of 1, so that's G30. I did the same thing for the Kw star. At this case, I divided the Kw by the activity coefficient of the hydroxide ion and the activity coefficient of the proton. So instead of putting brackets around them, I just divided twice because of the order of operation in Excel. All right, so now that I have values for Kb star and Kw star, I can use these ionic strength corrected values in my equation. So you may have noticed I was a little bit careless in defining cell B28. B28 wasn't really Kb, it's Kb star. And I did that because I want to include the ionic strength dependence. And similarly, if I look at H plus is the Kw star divided by the OH minus concentration. So this accounts for the ionic strength effects on the dissociation of water. Having done that, I can now come down and calculate the POH, and this is the negative log of the hydroxide ion activity. So notice I've included the activity coefficient, G29, and I've done the same thing for the pH. It's the negative log of the proton concentration times its activity coefficient. So those are all now defined correctly. And then finally, I have the alpha 1, alpha 0. Now I'm going to use the same notation. Alpha 1 is with one proton dissociated, so that's going to be the weak base form. And alpha 0 will be the acid form. So I'm using the same alpha notations as I use in a weak acid problem. And you see that in this weak base problem, 96% of the base is undissociated, and 3% of the base is the conjugate acid. So last but not least, we can now play around with our Kb. If we make the base stronger by making our Kb, say, 3, we expect the POH to go up, the POH rather to go down, the pH to go up, and these alphas to shift. So here we go. Change it to 3, hit enter. Sure enough, POH went down, is now smaller, went down. pH went up. Alpha is now 70% dissociated, or 70% associated and 28% dissociated. And notice now that our ionic strength is now considerably bigger. It's on the order of 2 millimolar because of the increased dissociation due to the increased strength of the weak base. So again, this is an example of doing a weak base problem with activity coefficient corrections. I want to eliminate that and just do it with assuming that the ionic strength is 0. I'm just going to put a 0 in, and now all of my calculations are done with gammas of 1. Notice now Kb, Kb star, Kw, Kw star are all equivalent.